Well, good morning. Okay, well today I want to continue where we left off on Chapter 5, QR factorization. And I didn't have a chance to post the next project, but I'll do that today. Okay, so we left off looking at the properties of householder reductions. So and the properties of QR factorization. Okay, and what I showed you was just the overview of the numerics. The idea is that you have a matrix and you've got a column of that matrix, and you want to annihilate everything in that column except for the first entry. And without loss of generality, let's assume that the first entry is non-zero already. And if it's not, that's very easy to force, because if it's zero, we can just permute a row into there and make it zero. So if it's all zero, well, then you've got a singular matrix. That's a different problem. But if there's any non-zero in this first row, just swap it up to there. And a permutation is also an orthogonal operation. It just flips. It doesn't change the length of a vector, right? The sum of the squares. If you take a vector and swap two of its coordinates, okay, you just change its orientation, you don't change the length. So permutations are orthogonal as well. And so it turns out if you want to annihilate a column like this, then the householder reflection that does that is well, householder reflections always look like this, and beta, this scalar, is actually 2 over V transpose V. And so the householder reflection is defined by this vector V, and it's that vector V that sort of defines the mirror, right? If you want to have this, if you have this vector here and you want to rotate it to another place here, then the vector V defines this. It's the vector that points out away from this mirror, okay, directly. That's going to rotate this vector or make it mirrored somewhere else. And as long as this first entry is non-zero, this is, and I'm not going to go into the numerical details of where this householder vector, how the householder vector is computed. I've got the code here. I've got it described there. What's important for our case is not so much how it's computed, but what the non-zeros in this vector are. And it turns out that V and X are identical except for the first entry. And in fact, this householder function on page 69 just takes a vector X and it finds a householder reflection which is defined by these two scalars, beta and V, such that H times X is all 0 except for the first entry, which must be the 2 norm, right? Because a householder rotation just takes the vector and moves it. It doesn't change its length. And so if it annihilates all the entries in X, basically it's now pointing this vector just along the first coordinate axis. So that must be the length of the vector, the 2 norm of X. And V and X have the same non-zero pattern. So if I let script V be the non-zero pattern of the vector V, and this is the pattern of X, then they have the same non-zero pattern if we assume that the first entry of X starts out as non-zero. If it's not, it'll be present in V. Okay. And V will then have one extra non-zero entry. And that makes the combinatorics rather awkward. And so that's why it's very convenient just to assume that basically what we're going to do is we're going to assume that the matrix has a zero-free diagonal. And equivalently, every vector as we annihilate it will have an entry on that 1, 1 position, on the very first position. And like I said, if that's not the case, we can always permute the matrix into this form, either on the fly or up front. And if we can't do it, then the matrix is singular anyway. So these two non-zero patterns, the pattern of V and the pattern of X, are the same. And so if we take this matrix and we grab the first column and we find this householder reflection that annihilates it, that's this matrix H. Well, we can't just apply it to the first column, right? You can't just take this matrix A, and we're trying to say solve a least squares problem, okay? So I can take this, I'll call it H1. So I can take, if I'm trying to minimize the 2 norm of AX minus B, that's my goal. Well, I can't just arbitrarily rip out a column and operate on it. I have to operate on this whole equation. And so what you can do is you can say, well, let's take this householder and apply it to all of this. And if you do that, then you don't change the 2 norm of the resulting residual AX minus B, because you've multiplied by an orthogonal rotation. And so you can basically take this H and multiply it on the left by A without any problem. As long as you keep track of the householders and apply them to B when you're done or as you go, for example. We don't know X. All right, that's the thing we're trying to solve for. But as long as you take H and either apply it to B as you go along or save up the householder vectors and apply them when you're done, then this modified system will still give us the same X. All right, I showed that last class, that multiplying by an orthogonal matrix will eventually, hopefully, lead to a system here, H1 times A, that'll be easier to solve. So we've got to take H and multiply it by this H1 here and multiply it by the whole matrix. So we want to know what happens to the non-zero pattern after a single householder applied to this matrix. But when we apply it to here, the first column is, say, H1A1. That's not a chemical formula. But if this is column A1, and if I choose H1 to annihilate the first column, well then H1 times A1 will look like this. It'll be all 0 except for the first entry. So I've succeeded then in annihilating these entries. Okay, now the question is, well, wait, we can't just operate on the first column. What happens to the rest? And so if we take this, we can, of course, think of the matrix as a collection of columns, A1, A2, all the way to AN. And if I multiply this by H1, I've got to do this to every column. So it's a separate problem, H1, A2, all the way to H1, A1. So now the question is, what happens if a vector is applied, if a householder reflection is applied to a vector from which it was not created? Okay, X is easy. The very first column is easy. It just annihilates everything but the first entry. Okay, we know what the non-zero pattern of that is. What's the non-zero pattern of the other things? Well, it's dependent upon this structure here. Okay, so let's look at H. Okay, and V and X have the same non-zero pattern. So there's several ways of looking at this. We can take H and multiply it by another vector Y and ask, so what's the non-zero pattern? To do this, you don't just multiply this as a matrix and do matrix vector multiplication. It's better to write this as the following, to expand it algebraically. Okay, and so this gives us Y minus beta V transpose Y. Beta is just a scalar, so that doesn't, and it's non-zero. So because it's 2 over the, this is the 2, V transpose V is the 2 norm of V squared, and V won't be of 0 length. So beta is not 0. But now let's ask ourselves the question, what is the result? What is the non-zero pattern of h times y? Well, this is more conveniently broken up this way. Y minus beta v times the quantity v transpose y. So this is a dot product. Well, you've done a dot product. You know how those behave. So now think about the dot product of, say, of this householder with, say, the second column. Now, this vector v has the same non-zero pattern as the first column of the matrix. And so what's happening here, we've got v transpose y. V is not x, but it has the same non-zero pattern as x, the first column, the column which we use to generate the householder. So v transpose times y will be non-zero only if these two columns share a non-zero value. If they're disjoint, it's 0. And if that's 0, the rest of it's 0, and y is not modified. So if I have a column here which is all 0 in just those positions, nothing happens to it. No change at all to this vector A2. Let's pick another one. Suppose A3, suppose this is non-zero, and who knows what these are. So suppose it shares a non-zero pattern. Okay, now what happens? Well, now this dot product is non-zero, because if I do v transpose times y, v has the same non-zero pattern as this first column A1, and if I do v transpose y of this column times this column, there's going to be a pair that matches. So that's non-zero. So it's some non-zero scalar. So now I'm taking the vector y and I'm subtracting. Beta is a scalar and this is a scalar. So let's throw those away. Pretend that value is just 1. Okay, because we're not concerned at the moment about the numerical values, just where the values are. So what I'm doing is y minus v. But wait, well, there's no numerical cancellation, so this might as well be a plus. And v is the same non-zero pattern as x. So the resulting non-zero pattern is the same as just y plus x. So if the two columns share a non-zero pattern, here for instance, then the resulting one, all these entries fill in. So any column which shares any one of these three non-zero entries has its non-zero pattern augmented with all three of them. Any column which has none of them will be unmodified entirely. So any column here, for instance, with, say, this non-zero, okay, will suddenly gain all three. Now, look at that. There's a very peculiar pattern happening, okay? There could be non-zeros down here, right, in the rest of this column. But look at the rows. What's happening to the rows of this matrix? This particular row, and this particular row, and this particular row, when we're done, all have the same non-zero pattern. Any entry that's, say, here, in this column, will suddenly find itself here as well. So if you have any of these three rows are defined by the non-zero pattern of the first column. So any non-zero in the first column defines a set of rows. Now consider those set of rows. And without loss of generality, let's just assume, for the sake of argument, that we permuted all those rows to the top. Maybe this is maybe perhaps easier to see. So there's the first column X, the first column A1. Okay. Then what's going to happen? Well, the first chunk of this is going to be zeroed out. So I'm just redrawing that matrix. I'm just putting those rows that are being modified up here, and the ones that are not are down here. So this is 0, so these rows are not being modified, but these are non-zero, so these rows get changed. And what happens to those rows? Well, there's two kinds of columns, right? So let's partition this matrix again into zeros here. Those are the columns like A2, for instance. See, it's 0, 0, 0. Let's just arbitrarily, just for the sake of the picture, put this column to the end. And let's put A3 right up next to A1. So these are the columns which share a non-zero pattern with the first column. I'm sorry, share a row index with the first column. And these are the ones that do not. These are the rows corresponding to the non-zero pattern of X, the first column, and these do not. So that splits the matrix now into 4 parts. Well, actually, I guess 6 parts, because this is the column A1, the first one itself. So this gives us a very specific kind of structure, because any non-zero here, now there's going to be, and you pick a column here, there's going to be a non-zero in this position, because that's how I define this submatrix. Those that share a non-zero pattern with this group and those that do not. So this is all 0, and here I've got at least 1 0. And of course, if I don't have any non-zero, I mean, this could be of empty size. Any one of these pairs, any one of these set could be empty. All right, so it's just because I've drawn both sets doesn't mean they both exist. These rows don't get modified at all, okay, because the resulting pattern here of what gets modified, it has the structure of y plus x. So we take this vector y here and just add to it the non-zero pattern entries that correspond to the non-zero pattern of the first column. So it's just these that get modified. And these stay the same. So what happens is here, there's no change to the matrix whatsoever. Nothing changes there. But within this part, and nothing changes here, because these columns don't get modified at all. Because this is 0. V transpose y is 0 for those columns. And now if you look in here, every time you see, you'll find a non-zero entry in this piece of the column. And then it gets spread to the whole rest of all the other columns. So this becomes all non-zero, completely non-zero. Do you see that? No. What don't you see? If there's a non-zero here, okay, that's the difference. So if I pick a column, this column has a non-zero in one of these rows, and this one does not. So this one has a non-zero pattern in at least one of these 4 rows corresponding to the non-zero pattern of the first column. Okay. That means the dot product of V, because V has the same pattern as this first column, and I haven't proven that, I'm just telling you so what the householder comes from. Because what's important here, as I said, is not the numerics, but the structural computation as to where the pattern, what the pattern is. So, but the dot product of this vector V and the vector here will be non-zero, right? And so this is a non-zero scalar. V has the same non-zero pattern as the first column. Beta is a scalar, so we throw that away and we're just doing y plus x. So this column right here gets replaced with, this is the result of h times y. We're taking h and multiplying it through the whole matrix, right? We're doing this. H times A1, H times A2, H1 times A, and so forth. So all of these vectors here, their non-zero pattern changes by the formation of the original vector plus x. So all of these entries get added here. Does that make sense now? So any non-zero here causes all of these to be added. So this becomes completely non-zero. You can think of this as, and I haven't looked at LU factorization, Gaussian elimination. In Gaussian elimination, okay, what happens is you have a pivot row and you want to annihilate things below the diagonal with this pivot row. Take this row and add multiples of it to zero these out. Right? Well, this is a very different kind of computation as to what we got over here. What we have over here is if there's a non-zero here and I take this row and add it to here, well, that becomes non-zero. And so does this. Okay. But if, for example, this is 0, then this can stay in some arbitrary structure because this is not modified. We take this vector and add it to here and nothing changes. So we don't have this kind of structure of some partial column that's, you see you have 3 entries here, but not all 3 appear here. But over here it's different. Here it's as if not only is the pivot row added to all of these, but all of these are added back to the pivot row. See, any row here is now replaced with the set union of all 4 of those rows. What is this that share? Think about this set of columns. What are those columns? Those are all the columns such that there's any one of these 4 rows has that non-zero column. Okay, so now consider the non-zero pattern of each of these 4 rows. We've looked at the columns. Now think of these rows. All of these 4 rows, what do they look like? Well, there's going to be, if you take the set union of all 4 rows, you'll get this set of share here. Because if there's a non-zero in that position, in that column, say for any given row, then this column will be in this group. So this set here is the set union of all those 4 rows. So what's happening then in the result is that once a householder is applied, any row which contains any non-zero in the first column, including the first row, gets replaced by the set union of all of them. All of them take on the same non-zero pattern, and they all take on the set union of all of them. So we take all these 4 rows, take their set union, and then splat that back onto all those rows that took part in that set union, and they all now have the same pattern. So it's a very, very special, very specific kind of operation that's happening. All the rows get replaced with the non-zero pattern of all the rows, this union of all those rows. And this has a pretty big implication for what happens then in the symbolic factorization. And it has a big implication for what happens in the both the numerical and the symbolic factorization. So let's look at this. So I guess these are properties which I've already defined, and I've just got them all listed here now. I've already gone through them on the chalkboard. So this is the form of the householder vector. We have a scalar scalar beta and a vector v, and we can choose v and beta based on some vector x, such that the first entry is the 2 norm of x and the rest is all 0. And this is how you implement a householder operation. You don't multiply through. This matrix is symmetric and orthogonal, and that's easy to derive. Given this right here, if you form H transpose, you'll see that it's just the same. So it's its own transpose. I mean, it's symmetric, and it's its own inverse. It's both symmetric and orthogonal. If a matrix is orthogonal, that means its transpose is its inverse, but it's also symmetric. So H squared is identity, in other words. And if x1 is non-zero, then v and x have the same non-zero pattern, and I'm just stating that just by the way the householders are computed. And if that's not so, we can make x1 non-zero. And so then QR factorization looks like this. We pick this h1 based on the first column to zero out that all but the first entry, and we assume that the first entry starts out as non-zero. And if it's not, it can be permuted to do so. And then we have a modified matrix, H1 times A, and now we've got a matrix that looks like this. We have a matrix now, all this is 0, and we have a slightly, we're moving towards an upper triangular matrix. Now, in the next step, we've got to be a little more careful. In the next step, I've got an entry here, and this is all 0. Okay. And I'm going to assume that this diagonal entry is non-zero. And I have to be careful here. Suppose, I mean, this entry, I don't know what it is, but it's possible it could be non-zero. Maybe not. If it's not, then it's not going to cause a problem. But if it is non-zero, I have to be very careful with how I deal with this. Let me just make this a smaller matrix so I can write it out in the following style. So we have to think of this as a 2x2 block matrix now, where we've got the first chunk of columns that have been annihilated and the parts that have not been annihilated. Because we don't want to mess these zeros up. Because if I apply a householder to this column in the middle, okay, and if this column shares any non-zeros with the first column, well then all these rows take on the same non-zero pattern, and this column becomes all non-zero again. Ooh, that's not good. I destroy my structure that I'm trying to introduce into the matrix, which is make it upper triangular. I'm moving that direction because I want to solve this linear system, or the least squares problem, with just a simple back solve. So I've got to leave this first column alone, and I also want to leave, I'd prefer to leave the first set of rows alone, although that's not quite as critical. And I only want to operate on this submatrix. So what I want to do is make up another householder, which looks like this. So if I do this, okay, and if you do the matrix multiplication, the outcome of this is that this first chunk of rows and this first chunk of columns is going to be unmodified because of this identity part and the zero part. So if you multiply this through, you just get x, you just get this chunk here plus 0, and you get, and so on. So what you end up having, if this is, I'll call this submatrix A11, A12, A21, which is 0, and A22, then the resulting product looks like this. A11, A12 is not modified. This 0 chunk is unmodified, and this becomes H2, A22. And so this is good because this leading matrix now, if this is, say, upper triangular, it's whatever it was is unmodified. And that's important because I don't want to obliterate those zeros, which is very, very easy to do. If, say, this is non-zero, then all those zeros get obliterated and we come back. We don't make any progress. But if I do this, then I preserve those, the work I've done so far, and I only operate on this. So H2 times A2 becomes a problem just in its own, just like the one I had here. I can think of it annihilating the first column of a matrix, namely the A22 matrix. So you just repeat. This is an iterative algorithm from 1 to the number of columns, just annihilating the first column of these submatrices, these trailing submatrices. And so that's what's happening here then. We've got this product of all these householders. We take A and we pound it on the left by H1 and then H2. Well, this H2 is actually has an identity in it and so forth, all the way down to the last one. And we end up with an upper triangular matrix. It's not too hard to show that if H2 here is a householder matrix, householder reflection, then this, and so it's orthogonal and it's symmetric. And certainly it's quite easy to see right away that, well, if H2 is symmetric, certainly this bigger matrix is symmetric. Okay. And it's also easy to show that if this is orthogonal, and I won't go through bore you with the details, I could derive it, I don't have it in front of me. But it's easy to show that if this submatrix is orthogonal, then this whole matrix is orthogonal as well. So we're taking a householder reflection and embedding it in a larger matrix, and we still end up with an orthogonal matrix. So we've got this product of orthogonal matrices here. And a product of orthogonal matrices is itself orthogonal. That is, if I take, and that's easy to show too, just with a bit of linear algebra. If I have two orthogonal matrices such that their transpose is their inverse, I multiply them together. Well, if I take that product and transpose it, I get them reversed transposed and multiply them together. The whole thing then cancels out. I get identity. So the product of two orthogonal matrices is itself orthogonal. Orthogonality is preserved when you multiply them. So I've got this product of orthogonal matrices. The result is all orthogonal. That's my Q, actually Q transpose. It's Q is the product of all these orthogonal operations. Basically collects everything together in a matrix form that we've done to our matrix A. And the things we've done to the matrix A is make it upper triangular. And so here is a MATLAB prototype of this operation, of this QR factorization. And it's right looking because what's happening is we're taking these householders and applying them then to the entire matrix as we compute them. So as I compute the householders, let's just multiply all of them through. Nothing wrong with that. It mimics exactly what I've drawn on the board right up here with this MATLAB prototype. So I start with a matrix V, which is going to be collecting all of my vectors. It's not actually a matrix. V, capital V here, is not really a matrix. It's a collection of columns, which is somewhat different. It's not linear algebraically a matrix. Every column, V in capital V, defines one of these householder operations. Okay, so we're just going to use it as a data structure, not as a matrix. Slightly, you see there's a difference there. So, and beta is just a collection of all of those scalar beta values for each of the householder. There's a MATLAB function. Oddly enough, it's inside the gallery. I don't know why they did this, but you can write your own householder reflection in MATLAB. It's pretty straightforward. But there is a householder reflection. There's a way of computing a householder reflection inside the MATLAB gallery function, and so that's what I've used here. So we take the householder, and by the way, householder is a name of a person, so it's not like it's not defined semantically because it's, I don't know. Anyway, this householder is constructed based upon the kth column and the entries on the diagonal and below. And it's chosen to annihilate it. And the 2, I forget what that's for. That's defining, I think, the kind of householder that's used. And that gives us 3 things. It gives us V and beta, which we're going to just stick in our data structure and just save. And it gives a value S, which I'd actually just discard in here. I don't even use it. S is just simply the 2 norm of the household of the 2 norm of this vector A. I just throw it away because I don't need it. And then this right here applies that householder to the entire matrix, which is written out algebraically in a better form. If I take this householder, okay, the same thing happens here. If I multiply this by an entire matrix A, then and this, by the way, is just a dense matrix algorithm. It's just doing all the computations, all right, for every piece. So just think of this dense matrix. Matrix multiplication is an n-cubed operation, right, normally. Let's suppose this matrix A is square. Here I've got it rectangular, but let's suppose it's square. So A is an n by n matrix. Let's pretend it's dense. We're doing dense QR factorization. V and V transpose is itself a dense matrix. Of course, it's going to be a submatrix. It's going to have identity here as we go along. But let's just look at the very first one. So the very first one's a completely non-zero vector. So V times V transpose looks like this. It's all non-zero. It's just a big dense matrix. Now, it's of rank 1. It's of rank 1 because every column is a multiple of all the other columns. Every column is a multiple of V. So, but other than that, it's a completely non-zero matrix. And if I form this first, if I take identity minus this dense matrix, I get a dense matrix. Now I've got a dense matrix to multiply times a dense matrix. That's normally an n-cubed operation. Matrix multiply is order n cubed. Well, we can do it in n squared. which is a whole lot better. And the reason we can do it in n squared is because we don't do it in this order, but we do it in this order instead. So h times a, no, I don't do it this order, I'm sorry. I do it in this order down here. What I want to rewrite this is as h times a as a minus beta VV transpose a. So multiply this through algebraically. So now I've got my original matrix. Matrix subtraction is n squared. So we can do that. But then the question is, can we compute this in n squared operations? And the answer is yes. Because V transpose times A is a vector matrix multiply. I can do this first. V transpose A then gives me, so V is a column, V transpose is a row. So V transpose times A is a row vector, which takes n squared work to compute, a single row vector. Now I get my matrix, V times this row vector. I get a matrix, which but this outer product is n squared computation of column vector times a row vector, takes n squared work to do. Multiply that times a scalar is also n squared work. Subtract it is n squared. The whole thing takes n squared work. So that's the way it's done here. We take the matrix and subtract that update, which is V transpose times the matrix itself that I'm modifying, and then multiplying through times V and beta, and we then subtract from A. So that takes n squared work. So the total work here, I've got order n work to compute. Well, it's order n minus k or m minus k here, but it'll be n work here and n squared work here. So the total work of this algorithm is n cubed, which is no different than, say, LU or Cholesky factorization. Its total work is n cubed. Now, this computation is very difficult to rewrite in a sparse matrix form, though. Okay, it can be done. In fact, a multifrontal method is a right-looking method. A multifrontal method is going to represent this matrix as a collection of dense submatrices. And here's my dense submatrix right there. That's rather convenient. I've got a collection of columns and a collection of rows, and all of them become non-zero. And so I could have a little dense matrix here that I say, look, I'm going to have my big sparse matrix A. I'm going to rip out some rows. Rip. And I'm going to say, look, all these rows have the same non-zero pattern once I'm done. And this chunk of the matrix is not modified, so I can leave that alone. And this piece of the matrix I can represent as a dense matrix, as a submatrix. That's called a frontal matrix. And I can, in fact, do the work inside this of the QR factorization. I can do this householder computation just inside this dense matrix. All right, that's a multifrontal method, but it's very difficult to implement, and the code is very lengthy, and so I don't have it here in the book. Instead, what I want to do is turn this algorithm around. I still need to compute all these householders, but now think about what's happening with these householders. You compute the householder how? Just based on the first column. And then you apply it and you zero it out. Well, let's postpone this multiplication of h times the rest of the matrix. Let's hold off. Let's just store h somewhere as a vector v1 and beta 1 and just leave it there. And now let's then go to the second column. Well, before we can compute the householder for the second column, I've got to apply the first householder to just it. Because this is an independent computation from all these others. This last column, these other columns, have no impact on the first column. So I can just postpone those matrix vector multiplies here for this householder h1. Just apply it to the second column. And then compute the householder h2 based on this. So first apply h1 to this column and then zero this out. And then when I come to the third column here, I just need to multiply through the previous householder operations to this column and then compute that third householder, and so on. So that's a left-looking method. Left-looking because at any given step of the computation, this matrix here is not modified, is not touched. We come to a column here, and when we come to a column, we look left and say, well, hey, give me all your householders that have been to the left of me, apply them to this specific column, I'll call it now column K, apply them to column K, and then compute the kth householder, and then advance to the next column. So we're going to advance from left to right. So it's a left-looking QR factorization, and that's this next slide. But now I'm going to start to exploit, let's see, now this doesn't yet exploit the zeros. I'll do that next. Okay, so this is a left-looking QR. It says, let's go through columns 1 through K. Let's grab the kth column, and then I have to go through and pull out from my data structure where I've saved all these householder vectors, and just apply them to that one column, and then compute the householder on that column, and then don't do anything with it except just save it. And also keep track of the kth column of R. We have to do that as well, because the kth column of the upper triangular matrix is this piece right here. Okay, so now we need to ask the question, and I think that's on the next slide. I already talked about this, what the non-zero pattern is of every row takes on the non-zero pattern of the first row, of all the rows that form it. It's already described that. So now we have to ask the question, well, what if it's sparse for this matrix, for this method here? What happens? It turns out then we don't have to apply all those householders. So if this is K, and it's a left-looking method, so we're going to compute a householder here, but we're going to postpone its application to the rest of the matrix. We have a non-zero diagonal. Let's assume that. Now, let's suppose this entry is 0. If this entry is 0, then consider this particular, let's call this I. Consider this householder here. Well, if this is 0, namely if this is 0 in the R matrix. So this is, if this is going to, if this is 0, not just at the beginning of computation, but in the resulting matrix R. So let's view this already as the non-zero pattern of R, the result after all the householders are applied. If after all the householders are applied, this is still 0, well then this householder that annihilated this must not have affected this row at all. Because if it did, it would have become non-zero because of this entry here. Because all the rows, well, it would have become non-zero at some point. Because if there's any non-zero below the diagonal, and this is where you have to assume that the matrix is a single connected component. But because if there's no non-zero behind the diagonal, then things change. But if there's any non-zero below the diagonal, okay, then but this thing remains 0. So this householder doesn't involve this column. If I drew this picture before, where I had, say, the first householder, I had it broken into these 6 parts, right? So here's a householder operation. And this is all 0. And these are the rows that get modified. Well, but this is 0. And if that's 0, then that 0 must be one of those zeros that says, look, this householder didn't modify this particular column. Because if there was any non-zero down here, it would share it. I mean, this would also have to be 0. Because if it was non-zero, that would be non-zero as well. So any non-zero here must reflect the 0 value there. Otherwise, that would have become non-zero in the matrix R. So this matrix R is telling us which householders have to apply. Here I'm just going through all of them and just applying them blindly. Okay, because it's just a dense matrix algorithm. When we start looking at the sparsity, we realize that, okay, this will be my kth column of the R matrix. If that's 0, then it must have been a column over here in the unmodified part. So it did not take part. That column didn't take part in the ith householder. Column K did not take part in the ith householder operation. And so that's a particular I that we could skip. So the householders that do take part, if this is a non-zero value in R, in the upper triangular factor, and if this is non-zero, well then this is an I which does have, it looks like this now. If this is the ith householder, now I've got a non-zero here in column K that it shares. And this is a householder that affects this column. This is one that doesn't. So the non-zero pattern of the kth column of R tells us which householders we have to pull in the sparse case, to modify the kth column of our matrix. So now we have to ask the question, what is the non-zero pattern? I mean, that was what we asked with Cholesky. What's the non-zero pattern of the result? Before we compute it, we'd like to know. So we're seeing a similar theme here. Before I compute this column, the kth column of R, and before I can zero this out, I need to know its non-zero pattern before I can find out which householders apply to it. Because this could be non-zero, could be 0 in the A matrix, but it could be modified and become non-zero, and then it could take part as a result. So I need to know here what the result is R, and that tells me the kth column of R tells me which householders take part in the factorization and in the operation on column K. So how do I find the non-zero pattern of something before I have it? That sounds familiar, doesn't it? We've seen this kind of question before. So now we got to ask the question, what is the non-zero pattern of the kth column of R? Well, the answer turns out to be very simple. You will have seen it before. I've got 3 minutes, so I have enough time to do this. In the end, we're going to have QR equals A. Well, if QR equals A, then A transpose is equal to R transpose times Q transpose. And R is an upper triangular matrix. So what happens if I take A and multiply that by, A transpose and multiply that by A transpose A. Then I end up with a matrix R transpose Q R, right? Just multiply these two equations together. Well, so far it's not really telling us anything, but now we know that Q is orthogonal. Q is its own inverse. So Q transpose Q is identity. This is just R transpose R. Oh my goodness, what is this now? R has a very specific structure. It's perhaps upper triangle. It could be rectangular. Okay, so this is R. Let me call this the R1 part, and this is 0. And so R transpose looks like this. R1 transpose 0. That's this matrix. So I've got this funny 0 block, okay, but I can ignore that because if I do the matrix product, this is just equal to R1 transpose R1. The 0 block just gets thrown away. It's just 0 times 0. Okay, we're done. But wait a minute. What is this? This is a lower triangular matrix times itself transposed. Oh, you've seen that before. That's called a Cholesky factorization of a symmetric matrix. This is an L, and this is an L transpose. You know what that is, right? Of what? Not of A, because A is rectangular or unsymmetric, but it's of this. A transpose A, which is, if A has full rank, A transpose A is certainly it's symmetric. If you multiply this, if you take the transpose of this matrix, you get itself. That's easy to show. And if A has full rank, this is going to be positive definite as well. This is a symmetric positive definite matrix, and there's its Cholesky factorization. And the L of the Cholesky is the R transpose. So all the theory, this is why this chapter comes after Cholesky, all the theory we developed to ask the question, what's the non-zero pattern of the Cholesky factor of A, suddenly gives us this non-zero pattern of R. It's just transposed. And so now, and I'm just out of time, now to ask the question, what is the non-zero pattern of R? The kth column of R? Well, if this is the kth column of R, that's the same as the non-zero pattern of the kth row of L. And we just spent weeks looking at that. This is the kth row subtree. That's all we got to do then. The kth row subtree tells us precisely which householder operations we have to apply to this kth column. So all the theory of finding the reach of the tree to find the kth row subtree for the uplooking Cholesky. This is in fact why I wrote the uplooking Cholesky to go with this sparse QR. In the uplooking Cholesky, you find the kth non-zero, the non-zero pattern of the kth row. Well, that's exactly the same thing here. Except now it's not the Cholesky of A, it's the Cholesky of A transpose A of a slightly different matrix. So anyway, we'll pick up, now that you see the connections, we can get into more of the combinatoric theory next class. And then this afternoon as well, I'll post the next project. So see you then. Thank you.